We'll work through the solution to Mechanical Engineering Statics at Dunwoody College. This is quiz 10. We have a beam simply supported. We have a pin support at the left end, a roller or bar at the other end to give it just a normal force. We have a distributed load that goes from 200 newtons per meter on the left end up to 400 newtons per meter on the right end. We're looking for the internal normal, shear, and bending moment at point C. And I've given you a rubric here, so you get pen. You get some points for a free body diagram of the whole beam. Get some reactions. Then a section beam, we get 2 points for that free body diagram. And then 1 point for each of the answers for the shear, bending, and normal forces, and 1 point for the work for those. So starting with our free body diagram of the whole beam. So we have our beam here. On the left end we have AY, AX. The pin gives us those two reactions. On the other side we get a normal force at B. It's only in the Y direction. Appears that we're horizontal. And then we have our distributed load. 400 newtons per meter on the right, 200 newtons per meter on the left, and point C is in the middle. So we can take this distributed load, break it into two resultant loads. So we're going to have one area where we have a rectangle right across the bottom. So you have 200 newton meters. Oh, I should put a 3 meters to this point and 3 meters to that point. Here's point C. So we have 6 meters times 200 newton meters acting right at the middle. It's a rectangle. So we have, I'm going to call it FR1, 1200 newtons. And then we have a triangle, that goes from 0 to 200, that 400 minus 200. And that's going to be 2/3 of the way from the left side. It's going to be closer to the right side. So it's going to be at 4 meters. I'm going to draw this in here. It's 1 meter away from C. And it's going to be 1/2 the base times the height. So our base is 6. Take half of that, we get 3 times our 200. So we get another 600 newtons here. That's what I was looking for our free body diagram. Now for my reactions, I only need what I need for solving this. I only get 1 point for a reaction. So I don't necessarily need to find all 3 of these reactions. I do need to find at least 2 of them. If I'm looking for the internal normal force, I'm going to need to find the X reaction at A. And then I'm looking for the shear force. I'm going to need one of the vertical reactions. So I can either do A or B in the Y direction. So I'm going to take I'm going to do the moments around B at first. I'm going to try to take the left side reactions. So our moments around B have to equal 0. So what do we have for B? Looking at a free body diagram, we have 600 newton acting 2 meters from B. And it's going to be a positive. It's going counterclockwise. Plus, we get 1200 newtons. It's acting 3 meters away. And then last we have minus 6 meters times AY. It's going to be acting up clockwise, so it's going to be a negative. Sorry, there we go. Trying to get that to be a negative. Oh, it's just going to fix it. So we get negative 6 meters Y. So this is 1200, this is 3600, so AY equals 1200, 3600, pulling this one around the other side, so we get 4800 newton meters divided by 6 meters, so we get 800 newtons. Got that bit. And then I'll do the sum of the forces in the X direction, 0, so we have AX equals 0. It's our other reaction. Alright, so I've got my reactions. Now we're going to take a section of our beam. So since I only found the reactions at A, I'll take the section of the beam from A to C, and we'll find our shear and bending and whatnot at C. segment AC. I have AY acting here, AX there. Oh, here's my distributed load on the middle point here. It's going to be 300 newtons per meter. This is 200 newtons per meter. There we go. This is C. So what are our shear, normal, and bending sign conventions? Our normal sign convention is going stretching our element. So we're going to have NC here. And then we're going to, if I can get all that to stay. And then our shear is going to be positive, is causing clockwise rotation of our element. So this is going to be V at C. And then our bending moment is going to make our beam smile. So we have that going counterclockwise. That would be M. All right. So I have this section. I went back to the distributed load. So I'm going to have, and this is 3 meters from here to there. So I have a 200 Newton per meter rectangle down here. So I'm going to have 200 times 3, 600 newtons. That's acting at 1.5 meters away. And then I have a 0 to 100 triangle. So I'm going to have 1.5, half my base of 3. One gives me 1.5 times my 100. So I get 150 newtons acting at 1 meter from C. There's my free body diagram for AC. I could have done AB. I'm going to stay with AC. It's a little easier. I've got that AX in here. So if we look at, now we do our equations of equilibrium. We'll start with some of our forces in X equals 0. AX is positive plus NC. NC equals negative AX equals 0. So NC is 0. Yay, there's one of our internal forces. Some of the forces in Y, 0. So we get negative 600 minus 150. These two parts of our distributed load. AY plus AY is 800. And we're going to have minus V. So I'm going to pull V to the other side. V equals 50 newtons. So I have 600, 750, and that negative 750 plus 800 gets me 50 newtons. And then last, some of the moments around C equals 0. So AY is going to be a negative moment. So I get negative 3 times 800 for AY. I have 600 times 1.5 meters for this part of the distributed load. I have plus 150 times, that's acting 1 meter away, and then M is going counterclockwise, so we have plus MC. Alright, so what do we get here? I'm going to put these down. Negative 2400, 600 times 1.5 is plus 900, plus 150. So what do we have there? We get 1050. So MC plus MC. 1050. So we get 1350. MC equals 1350 Newton meters. So our approach here, again, is we start with our big free body diagram, find our reactions that we need. I didn't need NB since I did segment AC. I could have chosen to do segment BC, and I would have found NB. I wouldn't have necessarily needed this AX then, keeping that segment in equilibrium. I just would have had NC equals 0. That might have been a smarter choice. So I started with that to get the reactions. Then I segmented my beam, or sectioned it at my point of interest, point C. Did another free body diagram for that. Applied my equations of equilibrium to find my internal loads.